an honor to introduce Professor M. Vikalekar. He is with EPFL since 2000. Right? Earlier he was at Bell Labs. He is recipient of IT Society Best Paper Award in 2001 and Teaching Award from EPFL.
Dries, thank you very much for a very kind introduction, and also thank you for inviting me here. Okay, so let me give you some examples. Okay, so this is so there's easy channels. So there's the first kind, which are the good kind. Okay, so suppose you have, let me make the discussion to be binary input channels. Okay. I'll input. So the first channel is the following. You may send a 0, okay, and the 0 might be received as one of these, let's say 4, 5, whatever, how many arrows I put, symbols. This is the standard diagram. I hope you're familiar with this, to represent the channel as being input on the left, output on the right, and you put a connection. If this input can lead to that output, you label these things with the probabilities that if you send this symbol, what is the chance that this symbol is received? I put here the number, this probability there. And if you send a 1, okay, then you have some complete disjoint set from the previous one of outputs. Let me call this set to be, let's say, y0, y1. These are the outputs that might be received if 0 is sent, and those are the outputs which might be received if 1 is sent. And you see in this picture that these two class sets are disjoint. So this is an easy channel because the receiver has, doesn't need to do anything. Just by looking at the y, he can determine what the input was. So you can communicate one bit of information every time you use the channel. The capacity of this channel is 1 bit. Okay, thank you, Kana. Okay, so the C is equal to 1. But not only is C is equal to 1, it can be achieved without coding. Okay, so capacity is 1 and can be attained without coding. Okay, all right. So these are perfect channels. Channels of this type are perfect. There's the other kind. Okay, I'm using too much blackboard, but okay, so I'll erase. Other kind is the following thing. So, for example, you send 0 or 1. No matter what you send, this symbol is received. Okay, so this is there's this symbol here. This particular y naught is received, no matter which one you send. Okay, or a more general could be the following thing. Let me denote the channels by W. This is the channel. Transition probabilities. More general, the statistics of the output does not depend on what you send. Whether you send a 0 or a 1, the distribution of the output that you're going to observe is the same. So for a statistician trying to decide on the basis of y, was it 0 or was it 1 cent, you have no basis of making a decision. Okay, so because the distribution of y is the same, no matter which of these 0s and 1s are sent, so the receiving of this y gives you no information at all about what was actually sent. Okay. So what is the capacity of such a channel? How much information can you send? Capacity is 0. Okay. Okay, so this is a completely useless channel. Okay. And the capacity is 0 also means that no coding is needed to achieve the capacity because there's nothing to achieve. Okay? So the coding unnecessary. You can transmit at capacity very easily. Okay? Even though, it doesn't do you much good, but you are perfectly efficient on this channel, no matter what you do. So again, no coding needed. Okay. So if the world consisted of channels only of these kinds, we would have no job to do. Okay, so we would close shop and go home because nobody would need any kind of coding theorists or communication theorists to deal with communication. Things are very easy. No coding is needed in either of these cases. We'll be fine. So I mean, fortunately for us, the world is not like that. There are channels whose capacity is neither 1 nor 0, okay, and they require coding effort. So now, the idea behind polar codes is the following. You give me a collection of mediocre channels, I'll try to convert them to channels of this particular type. So now, the conversion can be done if your only goal is to make these channels to be one of these two types. It can be very easy. I can take a mediocre channel, map all its outputs to a common symbol, let's say, as Kannan is suggesting, let's say the symbol K for Kannan, okay? And then I'll end up with a channel which is of this particular type. So the original channel maybe is like this, okay? But I take all these symbols here and map it into a single symbol. They can always do for any particular channel. I'll get a channel like this one, okay? All right. So I have converted the world into channels of this easy type, but I have lost many things. I want to do this conversion. I'm greedy. I want to ensure that the total capacity is preserved. Okay, so that's the difficult thing to do. So to convert the world into one of these two types is easy. It is difficult to do if you insist that I should do this without loss. Okay, so we shall see this polar codes, or the polar transform, maybe if you wish, does that asymptotically. Okay, so it doesn't do at the end. You never quite get these two things, but you get close to these two things. Okay? So that's the idea. All right. In a sense, I mean, we are solving the coding problem not by actually doing coding, but by a transform. Of course, there's a completely philosophical distinction, because at the end, all codes, in fact, create these channels behind the scenes. Okay? So every code that we know of is, in fact, at the end, a polarizer. So, but polar codes are a particular way of doing this thing in a systematic way. Okay? All right. Let me just say the polar transform, maybe. So what we do is the following thing. We're going to start with just 2 copies of our original channel, which might be mediocre. Okay? And we're going to create 2 new channels. I'll call them to be synthetic channels, okay, which will be closer to these 2 extremal cases. Okay? And the transform we'll do is extremely simple. Again, I'm in the binary world, so all the inputs are binary. So we have a channel W. So given a binary input channel W. So what does this mean, by the way? So given the channel doesn't mean that I have this channel only one shot. Okay? Having a communication channel means that I can use this channel successively. Okay? So this is, I can send x1 across it, and I can send, and y1 is received. I can then send x2 across it, x3 across it, and so forth, and the successive y's are going to be received over this channel. So we have, given this channel, the multiple copies come for free. Okay? So take 2 successive uses, let's say, of this channel. Y1 and Y2. This is 2 uses of the 2 successive uses of this channel. So instead of considering them the channel from x1 to y1 and the x2 to y2, I'll create 2 synthetic channels in an extremely trivial way. And the way is the following. I'm going to put here a XOR operation. All additions are done in the field of the channel alphabet. Okay, so this is modulo 2 addition in this particular case. Okay. And then I make these things to be U1 and U2. Okay. So note the following thing. This U1, U2 determines x1, x2, and vice versa. If you give me x1, x2, x2 is the same as U2. Okay. So you know U2. Once you know U2, x1 is U1 plus U2, so you can solve for U1. So from the x1, x2, you can determine U1, U2. From the U1, U2, you can x1, x2. So then nothing. Okay, so this transformation is not really doing, from an information theory point of view, one-to-one transformations preserve everything, so we have not anything at this moment here. But I'll view the structure in the following way. I will claim to have created 2 synthetic channels. Okay. The first channel is this one, the channel from U1 to Y1, Y2. Okay. So this is the channel. I'll call them for reasons that will become apparent. The channel W minus. Okay. So the original channel was W. My new channel I'm going to call W minus is the channel that connects U1 to the output Y1, Y2. Okay. So this I clearly have. So the input guy, the transmitter guy who controls these U's can control the U1, and the receiver guy who's sitting here is observing Y1, Y2. Okay. Now comes the slightly more tricky object. It is the following. The channel W plus is the channel from U2. Okay. And the output is not just Y1, Y2, also U1. Okay. Now, this is a channel from U2 into Y1, Y2, and U1. It's actually nice that the blackboard thing fell in here, because obviously this U1 is something very tricky. Okay? So this is a strange claim to have obtained such a channel because, well, U2 is no problem. The transmitter indeed sends it. Okay? So it is indeed input to this to the physical objects that we have there. Okay? And Y1, Y2 is indeed in the position of the receiver. That's fine. Okay? But how is the receiver supposed to obtain this U1? Okay? Because he obviously doesn't have it. Okay? It's on the other side. Okay? Now the idea is this. The idea is to say that, I'm going to decode the output of the W minus channel first. Okay. If I have a successful code, a good code for the channel W minus, okay, I can send my code word that I'm going to using for W minus channel, receive these Y's, decode what is being sent by the transmitter for there. Once you have decoded, hopefully correctly, okay, then you indeed have the U1 in your hands. Okay? So this W plus channel is a synthetic channel that becomes available only after you have processed the output of W minus first. Okay? Right? Is this reasonably sensible? Okay. So now then you should say that, okay, why aren't you putting here the estimate of U1 from, why don't I put U1 hat? Okay, right, excellent question. Okay, good. So because obviously what I have is not U1, but an estimate of U1. Okay. Let me make a small diversion for the benefit of Kanan and all the others, okay, hopefully, about the notion of Gini-aided versus unaided decoding. Okay. All right, so this is a diversion. Okay. So now, suppose you have the following situation. Suppose you have a bunch of U's. Suppose you have these bunch of these U's, okay, which influence an observation. Let me call this observation to be Z. Z in this case is the collection of these Y's, okay, the vector Y1 up to Y2 up to Yn, because we're going to do this many times. Let me, instead of writing all these sequence of Y's, let me just write a compact object Z. Okay. And now suppose we want to estimate these U's from the observation Z. And suppose we have this successive estimation strategy. Okay? So, right, we do this in the following way. We do this with the aid of a Gini. Okay? Suppose we do it do we know what Gini is? Because when I was a student, I didn't know what this Gini was. So people told me about Gini-aided arguments, and I was saying, what the heck is this? Gini is the following thing. If you watched, or if you know the Arabian Nights, you find a lamp, okay? You rub the lamp, okay? And this Gini appears, okay? And you ask for him, okay? He asks you, okay, what do you want? And then you can make wishes to this Genie. He grants them. Okay, that's the Genie. But the Genie is a strange kind of Genie. I'll tell you exactly how it kind of is. So in the following way, so from the Z, we make an estimate using, let's say, a function phi1. We make an estimate of, let's say, U1. Okay? This is our estimator for U1. Once we have made this estimate U1, this may be right or wrong. At that moment, the Genie tells us if we are right or wrong. Okay? So he actually tells us the correct value of U1, but only after you have made your guess. Okay? Okay? So he doesn't help you before, he helps you after. Okay? But now that we have the genie's help, we can estimate the U2 using some other function maybe, using z and the true value of U1. This is not the U1 tilde because the genie tells us this. Okay? We ask the genie, please tell me U1, and he says, okay, yes. If you ask him here, he says, no, I won't tell you before you make your guess. You make your guess first, and then I'll tell you. You can make your second guess with the aid of this one. Okay. Similarly, we estimate U3 using z, and at this moment, of course, after we made our guess as to the U2, the genie tells us the true value of U2, so we can use it in estimating U3. You get the idea, right? So Un tilde is phi n of z, and the true values of U1 to Un minus 1. Now, at the same time, we're going to put on this side a real guesser without the help of the genie. Okay? I'm going to same functions. I'll keep these. So I'm going to estimate. Now, these are my actual estimates, the hats that we had. Okay? U1 hat. I'm going to use the same function phi1 with the same argument. So in this particular case, the U1 hat and the U1 tilde are exactly the same. Okay? Because I'm using the same function with the same observation, I get this. Okay? But for the U2, I'm going to use the same function again, phi2, with the same argument z, but my estimated U1 there. So there's no genie for the right-hand side decoder. We go on like this. Okay, so U3 hat is phi3 of z, U1, U2, these are the hats. Okay, and Un hat is phi n of z, and a whole bunch of hats. So now, here's the question. Suppose it was the case that for some U sequence, this true U sequence, and the Z that you observed, the genie-aided decoder was correct. Okay, so this object, suppose you have the event that the tilted U's were indeed the same as the actual U's. What can you tell me about the hatted U's? You see, U1 hat, U1 tilde was correct. Okay. Consequently, U1 hat is correct. Since U1 hat is correct, this function that we compute is exactly the same function as we compute there, because the U1 hat is the same as the U1 itself. Okay. If these are the same things, then U2 hat is also equal to U2 tilde, which was also correct, okay, and so forth. So we know that if you make no errors with the genie, you will make no errors without the genie. Okay. Similarly, if the genie-aided decoder made an error, suppose that the U1 tilde was wrong, okay, then the U1 hat is also wrong. Okay. But suppose that the U1 hat was U1 tilde is correct, but the U2 tilde is incorrect. Okay. Similarly, then the U1 hat is going to be correct, and the U2 tilde is going to be incorrect. From that point on, God knows what happens. Okay. So, but the thing is, if you want the first index that the genie decoder makes incorrectly, is also the unaided decoder also decode incorrectly. From that point on, they're going to make different decisions. Okay. But if this guy decodes correctly, this guy decodes correctly. If this guy decodes incorrectly, he will also decode incorrectly on the block basis. Okay. So number of errors you make in the two cases might be different. So for example, if the genie decoder gets the U1 tilde incorrect but gets everything correct, okay, he makes one error among these U's. You get this one incorrect, and then all your guesses might be completely messed up. Okay, you might get many more errors here, okay, because there's no genie to put you back on the right track. So in general, you would expect that this guy will make more errors. It's probably true, okay? But at least the case that do you make errors or not are the same. If you don't count how many errors you have made, but just have you made any errors at all or no errors at all, then these two behave exactly the same way. So the block error performance of the genie-aided and the unaided decoders are exactly the same. Okay? Consequently, for the purpose of analysis, I can put here the U1. Okay? So putting here the U1 hat, okay, is the correct thing. But putting here the true U1, from the point of view of analyzing the block error probability, is exactly the same. Okay? Hence the reason for putting there the true value of U1. It makes the model much more simple, okay, but also is correct in the sense that the analysis that we do on the basis of this, of the true U1 is the correct analysis from the point of view of the block error probability. Actually, it's a good point to actually give an example as to what this transform looks like. Okay. Clear on this one, by the way? Are we happy with this discussion as to the successive decoding with or without genies? Okay. Suppose, for example, suppose W is a binary erasure channel. Erasure probability P. This is the erasure probability P. Okay? All right. Let us now try to see what kind of W minus and W plus do we get. Okay? All right. So let's take a look at W minus first. Okay? So we send U1. Okay. By the way, I'm going to assume the following things. When you use this channel U1 and U2, I'm going to assume that the two inputs that you send are independent and fair. Okay? So each of these U's are going to be binary, equal probability of being 0 or 1. Okay? All right. Okay. So the U1 comes along. Okay? So when we have the possible values of the Y1, Y2, make a table as to what these Y1, Y2s that you receive might be. Okay. So there are two possibilities, well, four possibilities, okay, for the two channels. Either both erase, or the top erases, the bottom one doesn't, or the bottom one doesn't erase and the top erases, or both of them erase. I'm not sure how sure I said them, okay, but all right. So the first possibility that both the channels erase. So W, maybe I should write what the W is. The W is like this. You can put either 0 or a 1, and either with probability 1 minus P, you receive exactly what you have sent, or with probability P, you receive a I don't know symbol, question mark. Okay? All right. So the possibilities are these. Either they're both question marks, okay? Or let's say Y1 is a question mark, but Y2 doesn't erase, so you obtain from the output of the second channel U2. Okay? Or the second one erases, and you receive the output of the first channel, but the first channel's input is U1 plus U2, so Y1 is not erased, so you get here from here U1 plus U2 as the first thing. Okay? Or neither erases, so you get U1 plus U2 and the U2. Okay? These are the possible values of the Y1, Y2 pair. Okay? So either they're both erased, or the first one is erased, Y1 is erased, but the Y2 survives. If the Y2 survives, it's equal to the input of the second channel U2. Or the second channel is erased, but the input of the first channel has survived. But the input of the first channel is X1, which is U1 plus U2. Or neither channel erases, so you get X1, X2 as the values of the output. And X1 is U1 plus U2, X2 is U2. Okay. So let's take a look here. In this last case, remember the channel input is U1. Okay. In this case, we can determine the input U1 by looking at the output. You know U2, you know U1 plus U2, you can add them together, you'll get U1 back. So this is equivalent to having U1. Okay. The channel has told you what its input was. Okay. Now this one is equivalent to not knowing anything, okay, about the input. This one, what about this? The channel input is U1. The output contains perfect information about an independent object U2. Okay. Is this useful in terms of U1? No. Kanan says no. Anybody disagrees? We should say wrong things every so often. It'll help. So you want to value, so U and the U, of course, are now different U's. You guys, okay, want to know the value of U1, okay, but the channel tells you very helpfully, well, I don't have U1, but I'll give you, okay, whatever, U2, okay. But U2 I'm not interested in at all, plus the U2 contains no information about U1 because they're chosen independently. Okay? So this is equivalent to an erasure. Okay? Now here also, okay, you want the value of U1, the channel very helpfully takes the U1, adds upon this independent binary fair coin flip. Okay? So if the value is U1 is 0, you get U2, okay, which is independent, okay, and distribution half-half. Okay? Or you get the complement of U2, that is also distribution half-half. Okay? So if U2 happened to be a biased coin, this would have been useful. But since U2 is a fair coin, this is completely useless also. Regardless of the value of U1, this object has the same distribution. It's a fair coin flip, no matter what the U1 is sent. So this also is equivalent to a question mark. Consequently, this W minus is also erasure channel. You either get nothing, no value, or the U1 itself. Okay? What is the chance that you get the U1 itself? Is when both channels don't erase. Okay? So the unerasure probability is the unerasure probability of the true channel squared. So this is a BEC, so this W minus is equivalent to a BE of erasure probability this. Okay? So for the channel to unerase, both channels need to unerase. Okay? So this is equal to 2p minus p squared. I think I did my math correct. I'm not sure. Okay. Somebody check. Okay. Now let's take a look at the W plus. Okay. So let me write this thing maybe separately. So the W minus is equal to this. Okay. Let's take a look at W plus. W plus is something similar. Now this time we have U2 as the input. And at the output we have these things and the U1. Okay. So output of W plus is the same as the output of W minus, but with additional extra information about the U1 itself. Let's now take a look as to what is happening. Take a look at the last row. Okay. The input to the channel is U2. The output contains U2 already. Oh, very nice. This is equivalent to U2. We already have U2 here. Okay. In this case, well, the input is U2, output contains U1, and also U1 plus U2, which allows me to solve for U2 by simply adding these two things. Okay. This is also equivalent to U2. Okay. This one, I have U2 in my hands. Okay. It's very good. Okay. Here is the only problem. You want U2, you get two erasure symbols and the U1, which is completely useless to you, okay, because the U1, remember, was independent of U2. So this is equivalent to the question mark symbol. Okay. So consequently, W plus, I did a blackboard in a terrible way, I'm sorry. W minus is here, so W plus is equivalent to also erasure channels, but the erasure probability, which is p squared. For this W plus to erase, both channels have to erase. Okay. And now I think we get to your question there also. You had said that how am I supposed to use the output of Y2 for W plus, W minus? In W minus, there's no this column is not here. But you see that you had to use the Y2 to be able to decode the actual thing. I had to XOR the Y2 and Y1 to be able to get the true value of U1. So the Y2, even though it seems to be saying something about U2 only, is necessary because U2 you observe from here, but the U2 corrupts your U1. So knowing something about this U2 through the Y2 is useful to you. Okay? So you cannot, in the W minus channel, you cannot ignore the Y2 because it is useful. Okay? Right? Similarly, for the W plus channel, you cannot ignore the Y1 because it was useful exactly here. Okay? Looking at Y2, you would not get anything, but the fact that you observe the Y1 helps you as to what to do. Okay? So the two outputs, both of them are useful to both the channels. All right. Okay. So we have P squared. So now, if you take a look at these things, okay, so maybe it's becoming slightly clear as to why I put these things plus and the minus. Because you see, if the original channel W was erasing with probability P, the plus channel is erasing with probability P squared, which is much smaller than P. If the P was, let's say, half, this is only a quarter. Okay? And if P was a half, you can check easily that the 2P minus P squared is more than P. That's a trivial exercise. And well, P minus 2P is bigger than P because 2 minus P is bigger than 1. Okay? Because the P is between 0 and 1, so 2 minus P is more than 1. So P times something which is more than 1 is more than P. So the W minus channel is worse. It erases more. W plus channel erases less. Okay? In fact, their average erasure probability, if you took the average of this number here and this number there, you get exactly P. Okay? So the overall erasure probability is preserved, but I have sort of created inequality. Okay? So in the sense of this coding, social justice is terrible. Okay? You want a world in which everybody is the same is very bad for us. Okay? So if you had a whole sequence of erasure channels, each of them erasing with P, is terrible. I'd rather have a whole bunch of people which erases terribly, they're bad, okay, and a bunch of people who erase very little, that's good. I want to distribute my total badness to concentrate among a few people. Okay? I'd rather have a whole number of very bad channels so that I can get a bunch of good channels. Having everybody mediocre is bad for me. I want to create injustice. Now, fine. Now the trick is now the following thing. So now we have seen, at least for the BEC, what happens. I'll show you these kind of things in more general. What I want to now do is the following thing. You see, this is true for most things in life. If you can do something, you can do it again. Okay? There's some things which cannot be done this particular way, but if you have some operation, okay, you can try to do this operation once more. And the good thing about this polar transform is the following. Remember, we started from a binary input channel, W, and we created two new channels, which also happen to be binary inputs. So the objects which come out of the transform are of the same type that we had started with. So there's a chance that we might be able to use the same transform on the things that I created now. Okay? So let's see what we would do. So the thing is, of course, remember, in this transform, I needed two copies of the same channel W to start doing anything. Right? So to be able to work on W minus, I need to two copy W minus. How do I get this? Well, the idea is this, that you start with two copies of W. We do our polar transform. Okay? This gives me one copy each of W minus and W plus. Okay? I need two copies of these things, so I make one more of these diagrams here. So I start with two copies. I start with, I cannot count it seems. I start with 4 copies of W. Okay? So now what I have here sitting is 2 copies of W minus, for example. So these two guys here, they see, these are the inputs to the 2 copy W minus, and these are the outputs of W minus. So I can combine them in the same way. Okay? So this was the okay. So now I have combined these two W minuses to obtain the one copy of the minus of the W minus, okay, and then one copy of the plus of the W minus. Okay. I also have sitting here 2 copies of W plus. They become available only after I decoded the 2 constituent W minuses, of course. We have to remember in which order we're supposed to decode. Okay, all right. But once I have done that, I have these 2 W plus channels, so I can also combine them in the same way. I can put here a plus. Maybe I should just do a straight line. And only connections are if I put a dot. Okay? So two lines crossing does not mean there's a connection. Only if I put a dot there, they cross. Like this. Okay? So now I've then obtained a copy of W plus minus and a copy of W plus plus. Okay? All right. So I start with 4 copies of W. I obtain 1 copy each of this guy, this guy, this guy, and this guy. Okay. Let me, for simplicity, write this one as being W minus minus. This is as being W minus plus, W plus minus, and this is W plus plus. Okay. So instead of all these parentheses, it'll drive me crazy. I'll just write the minus signs without the parentheses in there. They start from inside to out. Okay. Okay, so we obtain these things. Now, of course, now if you think of the case of the binary erasure channel, okay, of crossover of the erasure property P, this W minus was worse than the original one. Okay, this one in here. This is even worse. So this has bigger erasure probability than anybody else. This one, we took the P, made it to be bigger. This is a bigger erasure probability. And then we made a plus, we reduced it. So it is unclear at this moment what kind of channel is this. Okay. Similarly here, we make the channel better and then worse again. Okay. Here you make it better and better. That's fine. Okay, even better. But it's not completely obvious because of these mixing of the plus and the minus signs if you're indeed making progress towards the extremes. It is clear that this guy is getting worse and this guy is getting better. And I guess you will see now where I'm going, because now I'm going to do this thing one more time. I'm going to take this guy, take a whole copy of this thing again, all 4 of them, boom, in there. And then I have 2 copies each of this W minus minus, W minus plus, W plus minus, and W plus plus. I'll combine them 2 by 2. The 2 W minus minuses, I'll come down to be 1 copy of W minus minus minus, and 1 copy of W minus minus plus, blah, blah, right? So the channels with many, many minus signs on the top, they're getting to be worse. And all the plus signs are getting to be better. But things in between, minus and the plus and the plus and the minus, blah, blah, it's not obvious if they are going towards one of these extremal channels or not. Okay? So that's a question. Okay? Let me try to give a, there's not an answer, just to test to see what is happening. Right? When you enter the situations, you try to see, let me compute, okay, and then see what is happening. Perhaps we'll see something. Okay? So I'll do this computation. Okay, so let's write some code. Okay. What I want is, I want to work on the erasure channel. So I first want a code which does the following thing. Given P, I want something which prints P squared and 2P minus P squared. Okay, let's write that. Let me call this thing Pol. Okay. Let me just say P, just to make it to be nice. P times 2 minus P. So for example, if I take this Pol, if I put it 0.5, we get 2 numbers as input 0.5. We get 2 numbers. The P squared is 0.25 and 2, whatever it is. Okay, all right. So now, what I want to do is the following thing. Let me do this one, maybe just to make it nicer, for example. So if I feed 0.3 to this guy Pol, I'm calling it Pol, so we obtain the square and so forth. Now, what I could have done is the following thing. I could do this thing twice. Okay, so this second of these programs is now accepting the 2 numbers that came out. So the first number that you see here is the square of this. Second number you see here is 2P minus P squared of this 0.09. And the next 2 numbers correspond to the feeding 0.51. This. Okay. And we can do this thing. Let me maybe just do a just to save some typing. So this does 4 of these operations. So it'll take one number and produce 16 numbers for you. Okay, after this erasure probability 0.3 given to this thing and then done 4 consecutive polarization operations to obtain 16 channels, W with 4 minus signs all the way to W with the 4 plus signs. So it looks like I printed them with the plus signs in the top and the minus signs in the bottom. So this is after 4 consecutive squarings of 0.3. This is after 4 consecutive transformations 2p minus p squared to starting with point to 0.3. Now it's hard to see what is going on here. Maybe I should plot these things. Okay. Why not? 4. Okay. Let's see. I use strange file names, I'm afraid. Okay. That is. Okay. So on the x-axis is just numbered the line numbers, 1 up to 16. Okay, the first channel, second channel, third channel, etc. On the y-axis are these 16 numbers that were on the screen before. Okay. So some of them are very small. First number is here. Okay. And some of them are very big. Okay. I even have the pointer actually here. I can fiddle this thing around, but it's much less ugly. This is again not very informative. So maybe I should first sort these numbers and then plot them afterwards. Let's do that. I guess I should do this switch minus G makes it to be a numerical sort in general format so that something it'll understand these exponential notation. Otherwise, it'll sort them as being pure numbers. Okay, so now we see that these are now an increasing stuff. So we see a bunch of small numbers and a bunch of big numbers here. Okay. Now, still not very obvious as to what is going on. Okay. So maybe this 4 wasn't good enough. Let me do a few more of this stuff. Okay. So again, I start with 0.3. So I should now obtain 256 numbers, right? So each of these poll operations give you 16 numbers for each number that you feed them. Okay, so there's 256. Let me call it to be 8. Actually, let me also sort this. Okay, so now you see channel numbers from 1 until 256. And then now you see a whole bunch of very good channels. These are erasure probably close to 0. Whole bunch of really terrible channels, erasure probably close to 1. And then there is something still in between. There is a range of these indices for which the erasure probability is neither here nor there. Okay? Let's do one more step. What the heck? Now that we have started. Okay. Maybe I should do a few more and then we can see them in sequence. So this last one is going to contain 2 to the 16, 65,000 and something or the other numbers there. Let's plot that. What did I say? So now you see that we're getting much more sharper transitions. Okay, so a whole bunch of very good channels, whole bunch of very bad channels, and the fraction of neither here nor there channels have become fewer. Okay, so if you take from the total 65,000, only this narrower range in proportion has now remained mediocre. And you can also guess, since the total erasure probability is preserved, this transformation was keeping things constant. So the sum of these numbers is supposed to add to the thing that we started from, multiplied 65,000. So if indeed this was completely vertical, since I started with 0.3, you should see that 70% should be 0, 30% should be 1. Okay? So from a channel erasure probability 30% channel, I create 70% excellent channels, 30% terrible channels. Okay? And the communicators become very easy. I'll send my data on these channels, which are very good, okay? And then send no information at all on the bad channels. Okay? Let's go through one more thing. It's going to make the plotting more difficult. Computation is easy, but the plotting program needs to read all these numbers in to do anything at all. So let's go one more step. So there's going to be 1,000,000 channels now, 2 to the 20 channels. So it's going to now compute 2 to the 20 of these erasure probabilities. Okay. You see, it's not particularly difficult either. So this is all running on a few years old laptop with and scripts. There's no compiled programs here. Everything is done in shell script, which is extremely inefficient. This might take a few seconds because I should have plotted only every 10th number or something like this. Would have been okay. But you see, again, the transition has become even steeper. It's easy to make this thing go, I mean, if I go to 32, then I create gigabyte-sized files. So I cannot go much more because the hard drive is going to essentially die on me if I go to, let's say, 40. Okay, I don't have a terabyte amount of space here. So, but the computations are particularly difficult to do. So now what we see is, at least empirically, experimental-wise, this transformation, even though we were not sure as to these plus and the minuses, maybe they're not making progress towards these two extremes, it looks like they are. Okay? So this gives reason to think as to perhaps I should try to prove that this phenomenon is happening, that at the end, after many iterations of this polar transformation, maybe I am creating lots of these extreme kinds of channels. Perhaps it's a good place to stop because we made the experiment, and when we come back, maybe we could try to see how we might go about trying to show that this phenomenon is happening or not.